So until now, we studied how to translate the C programs into IR and how to perform optimizations on the IR representation of the programs. And as the final stage of the compiler, we're going to study how to generate assembly from the IR. So as a first step, we are going to study the assembly itself, and we are specifically focusing on the RISC-V assembly architecture. So we're going to study a few instructions there and how to compile C programs into this assembly there so that you can start working on these assembly generation from IR to RISC-V. So you first need to study a few vocabularies, and there are a few. So the first word to learn is assembly. So what is assembly? Assembly is basically the interface between software and hardware, and it is at the edge of the software. All software is written in assembly or higher level languages. And it is also on the edge of hardware. So hardware provides an interface that is assembly language or lower. So this is basically the where software meets hardware, where they are collaborating with each other, where the programs are represented, and where the programs are executed on the hardware. So in the current generation of computer industry, all software is translated first to assembly. So either it is executed on top, just on top of assembly, or it is executed on some virtual machine like a Java virtual machine or .NET virtual machine. Every executable code is first translated to assembly and then executed. And this is directly runnable on machines like CPUs and GPUs and some devices like network interface cards or accelerators. So not only CPUs, but also GPUs and other devices has their own assemblies. So we need to compile the programs into those assemblies in various kinds of these devices. So this is the assembly. And in this course, we're going to focus on only CPU assembly, and in particular, we are going to study RISC-V assembly, which is new kinds of CPU architectures. And the next term to learn is ABI, or Application Binary Interface. So assembly is the interface between software and hardware, right? And ABI is the interface among multiple assembly programs. So suppose that you are going to compose multiple assembly files into one executable. So it happens all the time when you are having multiple C programs, C files basically, and you compile them separately and then linking them together. Then when linking them together, you have to somehow have some interface among the assembly functions of multiple files. So that interface is called Application Binary Interface. So it is more of a historical term. So just please memorize it. ABI is interface among multiple assembly programs or multiple assembly files. So one particular aspect of this ABI, and one of the most important aspect of this ABI, is calling convention, which is describing how to send arguments and receive return values for a function. So suppose that a function f is calling a function g that is residing in another assembly assembly file. Then you have to somehow pack your arguments, right? Pack your arguments into somewhere and send it. And then at the end of the function call, the return value should be somehow turned back. And this calling convention is describing how to send and how to receive the values to the other function. Also, in addition, so these assembly programs are directly manipulating the architecture registers. And some registers are owned by the caller, and some registers are owned by the callee. So this calling convention is describing who is owning which registers. So all the details will be described later in another video. But let's just say that calling convention is attributing each register to each owner. Okay, and another aspect of this ABI is how to represent higher level function type. I mean higher level language types onto assembly. For example, in C you have struct. You have structure of multiple fields, and it is really important to decide how a struct is laid out in the memory or laid out in the assembly program languages. So that determines how to put which values to which memory locations. So that is decided by, again, ABI. So C types, C++ types, or Rust types, or other language types should be represented like this. That is described in this ABI. So studying assembly and studying ABI is a little bit different thing, pedantically speaking. But for the purpose of this course, we are going to say we are just going to study assembly and ABI at the same time, because for the purpose of compilers, we should generate assemblies that are satisfying the ABI specification. So we can regard them as a single language, assembly plus ABI. So we are going to generate only those assemblies that satisfies this ABI specification. That's the reason why we are going to study assembly and ABI at the same time. So let me move on to the next term, which is RISC-V. RISC-V is a new architecture that has emerged about 10 years ago as an open source alternative to the proprietary architectures like x86 or ARM. So it is open source, and furthermore, it is clean slate in the sense that it is built from the beginning without any legacy that should carry on. So it is built from the scratch without any support for backward compatibility for the existing legacy software. So it is a new architecture basically. And furthermore, it also provides an open source microarchitecture implementation. That means that it also provides an open source implementation of CPU on the RTL level. So it is describing a Verilog code that is describing the hardware configuration of an RISC-V core. So x86 or ARM cores are proprietary and it is not open source. So you cannot just use them because it is closed source. You cannot access them without proper permission, and you cannot use them without proper permission. But on the other hand, RISC-V cores are open source, and you can take the microarchitecture implementation for free without any loyalty. That's the new wave in the architectures, and it aims to be used for embedded systems like some IoT sensors, and also it aims to be used in the server market as well. Like these days, ARM and x86 dominate the market for both embedded embedded system market and server market. But RISC-V is aiming to somehow invade such a market and get some share from ARM and x86 on those markets. We will see whether RISC-V will succeed or not, because it is not yet widely used, but many have many interest in these new architectures. So I'm also interested in this architecture, so that's the reason why I'm demanding you to write a compiler for this RISC-V assembly. And another reason we chose RISC-V is that it is the easiest one to implement the compiler for. So it has much shorter language of definition than other architectures. ARM and x86, for example, has tens of thousands of pages of architecture definition. So each instruction is doing a lot of things. So each instruction has multiple pages of descriptions in this architecture. But on the other hand, RISC-V is a clean state implementation of an architecture and microarchitecture. And as a result, it has much shorter language definition. It has only 200 or 300 pages of language definition, so it is much shorter and it is much easier to target on for a compiler. That's the reason why we chose RISC-V. Okay, this is a new architecture we are going to study. So in a separate video, we are going to study the RISC-V code for a few programs and line by line, so that we can study the instructions of RISC-V easily. And in such a study, this Compiler Explorer will be very helpful. This gotbolt.org is an online compiler on which you can compile C programs onto a RISC-V assembly. There are multiple targets, and thus you can choose a RISC-V blah blah for your target. Then click some button. Then the C program, the given C program that is editable online, will be compiled to RISC-V assembly. And there also will be line by line matching. So it visually shows which line in the C program is translated to which lines of RISC-V assembly instructions. So it will be very helpful in learning these RISC-V architectures and instruction set architectures, basically. So you are going to study the RISC-V using this Compiler Explorer. So I'm going to show you this in a separate video. So in a separate video, we are going to walk through an introduction to RISC-V by Cheon-myung, who is the TA of this course. It explains RISC-V assembly and its ABI. And also, in another separate video, we are going to study this file, assembly-mode.rs, which defines the assembly AST inside the KCC compiler. So you're in the forthcoming homework, you're going to implement ASMGen that is translating an IR into the assembly AST that is defined here. So in a video, we are going to study this, and then you are going to implement a compiler that is targeting on the assembly defined here. Okay, that is the materials. Then it is the homework, assembly generation. Then its motivation is, so at the final stage of the compiler, we need to bake some assemblies from IRs that is actually runnable on machines. Then I'm going to show you some machine that is actual RISC-V hardware that actually executes your program. Isn't it cool? I mean, your compiler is used to compile some C program, and the result will be run on your machine. So that will be cool, I think. And the idea here is that you can do homework like this. You can, given a C program, you first go to the Compiler Explorer and see what happens when it is compiled with GCC or Clang. And we are going to do whatever they do in KCC. You implement something in KCC that exactly do the same thing with GCC and Clang does. So the challenge here is reverse engineering. You are going to find some examples that is suitable for exploring the compiler, assembly generations design, and execute it on the Compiler Explorer, and see what it does, and do exactly the same thing. So it is reverse engineering, and it requires some effort. So I think that's a challenge. But the idea is simple. Idea is just mimicking what they do. And you are going to be able to test your own implementation by executing this. So this is not yet implemented, but it will be provided soon. So please wait for a few days more for us to prepare for this. And it is basically checking if an IR execution's results and the generic code's execution results are the same. And as usual, you're going to submit your assembly generation to this GG, so which will be provided later. So historically, this path that is generating assembly from IR is called CodeGen. That means the assembly code generation. But I'd like to use an alternative name, which is assembly generation, because it better conveys the idea here, generating assembly, instead of generating code, which can be somewhat vague, because C is also code, IR is also code, but here we are actually translating IR to assembly, so that's the reason why I'd like to call it assembly generation rather than code generation.